Good morning, everybody. This is Mr. Steele, and I apologize for the fact that even though I'm not here, I am actually going to be teaching you anyway, and you don't get to miss out on a lesson, so sorry. But basically the idea is I'm using a time machine, obviously, as you can tell, because I'm not here, and yet I'm still speaking to you, and as the date clearly indicates right here, it is Wednesday, January 9th, 2013. So clearly this is a time machine. Congratulations, you've just witnessed the first successful use of it in the history of mankind, so you're welcome. But anyway, we're here today not to talk about time machines because, again, like the Nobel Prize Committee is very picky about people that talk about their inventions ahead of time. So instead, what we're going to talk about is we're going to talk about summation. So now, the reason that I'm really teaching you this today is because it's a fairly simple thing that you've seen before in pretty good detail back in Algebra 2 or Honors Algebra 2 for most of you guys. And I wanted to be able to go through this in a little bit of depth, just kind of going through it a little quickly. Talking about some of the big ideas, giving you some information to have in your notebooks, as well as obviously the one piece of information you've already been handed, the little half sheet, and then just kind of go through a couple examples and then lead you to the point where you can kind of see, okay, why would we want to do this? Like, what might there be? What value might there be in being able to use summation notation in calculus? Because, not everything is a derivative, unfortunately. So, what we're going to do today, as it says here on the notes, for the essential question, we're trying to figure out what is that weird E thingy. If you don't remember that, obviously we'll talk about that in just a second. That's what we're going to talk about right here. Talk about the notation we use for summation. We'll talk about how we can use it fast and how we can execute a summation in really quick order. And then, of course, why we might need it in calculus. Like, we just want to kind of touch on that just a little bit. I'm hoping this will go pretty quickly, but I've said that before, and then pretty soon we're out of time, and everyone's kind of going, oh, wow, there was no time for homework at all, was there? Sorry. So anyway, here we go. We're going to talk about notation for summation first. So to start off with, I'm going to give you a whole bunch of information, and then I'll just kind of talk about it and kind of add to it a little bit as we go. So first things first is when we talk about summation notation, we are talking about sigma notation. In fact, that big E thingy we were talking about just a second ago, that E thingy is the sigma symbol. It's just I don't remember exactly what letter it is in Greek. I think it's probably an S, but I'm not 100% sure. And it basically is a way to say, hey, you, add up all these things. Do it now. And so that's all it is. It's a way to say that we're going to summate a bunch of stuff. We're going to add a whole bunch of stuff up together. So I've written out here what a typical sigma would look like. And basically there are a couple different parts to this sigma thing. So first of all, we talked about the sigma itself. That tells you that we're going to add. Like, that's just kind of a thing to say, hey, add. But then from there are a couple different pieces. So the thing in here, the a sub I, it is technically the ith term of the sum, but in reality it's more like the formula, or as a lot of teachers, including Ms. Nakamura, talk about, it's the rule for what we're going to use to find the summation. It's the thing that tells us how to find the individual terms in our sum, or in our series, or the individual terms of the sequence that we're going to add up and make into a series. The letter down here, this little I, that's actually a variable. It is a variable, unlike n. N is actually going to be a constant. But I is called the index of summation, and it's just saying what variable we'll be using in here. It's saying which variable is like the quote-unquote counter. You can't see me right now, but I'm doing those quotation marks with my fingers. And that's exactly what it is. It's just kind of a counter. So it's something that we'll end up substituting in the values 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And that little index of summation, basically, what numbers we plug in, are determined by the bounds of the summation itself. In this case, the lower bound is this little 1 down here. It's saying start with I equals 1, so plug in and find a sub 1, the first term, and then add up every term in between up until we hit to the upper bound, a sub n. So those guys are basically the values we're going to substitute into the counter. There are counting values. So if we look at this summation here, the sum from I equals 1 to n of a sub I, what we're going to do is we're basically being told by this thing that we're going to add up first a sub 1. I should see if I can do this right. First we're going to add up a sub 1, then, okay, this is really annoying, so I'm not going to do that anymore. Then we're going to add up a sub 2, then we're going to add up, a sub 3, then we're going to add up a sub 4, and then we're going to add up a whole bunch of other numbers, or maybe a few, it depends on what n is, all the way up to, we get to the last term, just kidding, until we get to a sub n. And that will then be our summation. We'll have added up the first term, the second term, the third term, the fourth term, and every term in between up until the nth term. In fact, a sub I is sometimes called a discrete valued function because the values of I, of the index of summation, are determined by the counting numbers, so they're only whole numbers that go in there. But that's neither here nor there. It's just fancy math talk for when you take number theory, because all of you are so thrilled about math after calculus that you want to take number theory. Either way, though, what we've got here is just kind of our notation. This is how we're going to talk about it. And why are we going to talk about it using sigma notation and all these little things? Well, mostly we're going to do it because it's a lot quicker to write it out rather than saying, hey, you're going to add up a sub 1, then you're going to add up a sub 2, then you're going to add up a sub 3, then you're going to add up a sub 4. Hey, why don't you add up a sub 5? And then you just keep doing this, and then pretty soon people hate math and calculus, and you're being accused of being a witch and being drowned, because that's what they did to mathematicians back in the day. Look it up in a book. So anyway, there we go. That's our notation. Now, of course, what can we do with this, or how might we be asked to do this on, say, I don't know, the homework tonight? Let's take a look. So, magically, what do we have here? Well, we have a couple examples just really quickly to emphasize the idea behind summation notation. Now, obviously, I'll give it with the disclaimer that I'm going to do these the old-fashioned way of just kind of using the fact that summation says to add up a whole bunch of different stuff, a bunch of individual terms, and then I'm going to go through, and after doing this, I'm going to give you all the shortcuts. Well, you already have the shortcuts, but then it's neither here nor there either. So, basically, to start out with, just kind of emphasizing, okay, what does this all mean? Let's get the idea of summation in our head, because we've got to understand summation really means just adding a bunch of stuff over and over and over again. So this first guy, for example, let's look at part A, or example A. This one says to evaluate the sum from I equals 1 to 7 of I plus 3. Basically, what we're seeing is this is the formula that tells us how we can find, this is the formula that tells us how we can find the individual terms in the series. And then, of course, this is telling us to add up the first one, the second one, third one, fourth one, fifth one, sixth one, all the way through the seventh one. So we're going to, in fact, in this case, add up 7 terms in this series. Not just because it's a 7 up here, but because from 1 to 7 there are 7 terms that correspond. So, of course, what would we do if we had no shortcuts half sheet yet? So what would that look like? Well, basically, first we'd say that, okay, well, let's evaluate this out. We need 7 terms. So we need one for a sub 1, we need one for a sub 2, we need one for a sub 3, a sub 4, a sub 5, a sub 6, and a sub 7. And then, of course, we're going to go through and we're going to add up each of these individual guys, these terms, until we get our sum of a sub 1 through a sub 7. So again, all we're doing right now is we're using that definition that we used right here. Like we're just using it and putting it into action with an actual a sub I instead of just a. So of course, how do we do that? Well, first we're going to plug in I equals 1. That's all we're looking at right there, is I equals 1. So if I equals 1, then I plus 3 is 1 plus 3. When we go to a sub 2, that's going to be 2 plus 3, because we're just plugging in this case, whatever the counter's value is. For the next one, it'll be 3 plus 3. I'm going to stop pointing to it and writing I equals, because I trust that you've got it. Next one will be 4 plus 3, then 5 plus 3, then 17 plus, just kidding, it's going to be 6 plus 3, and then, of course, 7 plus 3. Well, what they have at the end is 1, 2, 3, 4, 5, 6, 7 individual terms that we're all adding up together. Of course, what do we get when we add them up? Well, that's not quite as important, but obviously we get 4 plus 5 plus 6. I should spread this out more and make it look nice. 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. And of course, we all know that that is going to add up into 49. Yeah, you thought I was going to say 42. Not so much. So there it is. It turns out that this sigma notation, the sum from 1 to 7 of I plus 3, is actually equal to 49. I mean, who knew? So there we go. That's actually the value of the sum of the first 7 terms. So this next guy, we do pretty much the exact same thing. Thankfully, I've changed it from the example I used last year, which was like I equals 1 to 19. Like, that's dumb. Why would I want to add up all 19 terms in front of people? That's stupid. So instead, I've got it going from I equals 1 to 5. So what do? Well, we do basically the same thing. We need one for a sub 1, we need one for a sub 2, we need one for a sub 3, we need one for a sub 4, and last but not least, in fact it's going to be the biggest because we're increasing, we need one for a sub 5. And we need to go through and plug it in. We need 1 squared, we need 2 squared, we need 3 squared, we need 4 squared, and we need 5 squared. And of course, when we add up those 5 terms, 1 plus 4 is 5, plus 9 is 14, plus 16 is 30, plus 25 is 55. Is that right? Did I do that right? 41, 50, 54, 55. We get that our value is 55. And of course, all my answers are subject to arithmetical mistakes because that's what I could have done. Either way, though, the idea is if we want to use summation, we're really just adding a bunch of stuff together. So in reality, no matter what the sum is, you could always just brute force your way through it and just add up a whole bunch of little pieces of something. That will always get you through that. Now, of course, you're in calculus, you're smart, you're bright, you have lots of demands on your time. I don't want to be the one that makes you sit around adding up the sum from 1 to 19 of I squared plus 3i minus 7. Again, not my goal. My goal is to make you just do things quickly. Like, I love to teach you efficient things. Which brings us to that half sheet that you already have. What are the ways we can do this fast? So let's take a look at that next. So here we go. First, as you can see on your half sheet, it's kind of separated out in, like, I'd say probably 2 pieces. There's that first row and then there's other 3. And the formulas get kind of complicated as we go down. Before we get to the more complicated ones that I'll give you some ways to remember a little bit quicker, tell you exactly what you need to memorize, I want to start with just kind of the basic rules. So what is this basically telling us? So this first guy is basically telling us that if you're adding up a constant, like this is like the sum of constant term, so think of it in terms of constants. Basically, what do you get if you add up a constant number of something? And the idea is basically you just multiply it times the number of terms. The reason for that should be pretty simple. So let's look at this illustrated really quickly. You might want to write this down, you might not. So let's say we're multiplying or adding up the sum from I equals 1 to 4 of 10. Well, basically, if we think about what that sum actually looks like, we'll see that it really amounts to just the first term plus the second term plus the third term plus the fourth term. Well, you notice there's just 1, 2, 3, 4 10s sitting here. So we basically just take whatever that constant is and we multiply it times the number of terms in order to get our sum, the value of our sum. So basically, so just add up the constant that many times. And when you add up the same thing a number of times, you can just basically simplify it to multiplication. This guy is basically the entirety of your 3rd grade arithmetic. Or I don't know, maybe it's preschool nowadays. They've accelerated you guys a lot. So there we go, first guy. The second one, this is basically your scalar multiple. And this one is also pretty easy to visualize if you actually write out a single sum. Basically says that if you're multiplying the inside rule by some sort of scalar multiple, so a number, basically it has to be a number. It doesn't have to be a whole number, doesn't even have to be a positive number, but just a number. It says you can basically pull out that thing and evaluate the sum with that scalar in front and just multiply your sum by k. So let's think about this a little bit too. So first let me shrink this. Try to get a little bit better at this as I go. There we go. So for this guy, if we're using the scalar multiple one, let's say we're adding up the sum from I equals 1, 2, 3 of, I don't know, let's go 3i. So we're adding up multiples of 3. So what would that look like? Well, first of all, we'd have 3 times 1 plus 3 times 2 plus 3 times 3. We can see that that ends up being equal to 18. Should make some sense. I mean, it just comes out pretty quickly. Basically, though, this thing says that we could do it a different way. We could write this thing as 3 times the sum, I equals 1 to 3 of I. Why? Well, basically, it's like we factored out that 3. And in fact, that's what we get. If we multiply 3 times the sum of I, well, that's 1 plus 2 plus 3. 3 plus 2 is 5, plus 1 is 6. That equals 3 times 6, which equals 18. So it's basically another way to evaluate a sum. And we will be using this, actually. Like this kind of method that I'm using, we won't do it exactly, but we will be using this idea as we go through. So scalar multiple 1, also pretty useful. It's a way to simplify it a little bit as we go through. Finally, for this guy, this is just basically saying we can add and subtract sequences or sums just like we would expect them to. Kind of like the limit stuff. Like it's the same idea. Like it works really nicely. So this is like the sum and difference of summations. So again, what would that look like? Well, it basically says, and I'm not going to do the work this time because I'm kind of bored with it already myself, and if I'm bored, I imagine you guys are bored. If we want to take the sum from I equals, let's go 1 to 3 of 10 plus 3i, we can actually separate this out into 2 pieces. We can go sum from I equals 1 to 3 of 10 plus the sum from I equals 1 to 3 of 3i. And that sum then will be equal to the sum of those two individual series. This one's going to be 30. Notice I changed the upper bound that we're summating over. We're summating to. This one's going to be 30, plus we already know this one's 18. We get 48. And then, of course, that means that this guy is equal to 48. So it's just another nice thing that we're going to use. In fact, basically all of these first three rules allow us to, I'll put it in big people words, it allows us to decompose a summation, at least a polynomial one, into something that we can work with a little bit better. Because obviously when you have these big long things, it takes a while to write out all the individual terms, and you're not going to have a good time if you have to write out all the individual terms. So these are all our methods to break stuff down. The next rules are like the super shortcut rules. So let's look at them next. Well, so what you're looking at here, I think they're number 4, 5, and 6 on your thing, but in reality what we've got is basically the last three properties that we're going to want to use when we're evaluating summations. We will be evaluating summations. So basically these are the shortcuts. Like these are the ways that you can avoid having to add up things a whole bunch of times. And when we get to stuff like, I don't know, infinite summation, dun dun dun. When we get to that stuff, obviously you're not going to be able to add up an infinite number of terms. The tests only allow you for 90 minutes. So unfortunately you'll need to have a shortcut. So these guys are things to memorize. Like you do need to memorize these guys. Unfortunately I can't judge my space enough, so I'm just going to write it this way. Memorize. So you need to know these things like the back of your hands. I will expect you to be able to evaluate these things without a calculator. Not always, but a lot of the time without a calculator. So now you're getting the formulas like they're just here. We'll use them as we go forward. But in fact, sometimes this form isn't as useful as other times. I sometimes like having a different form. Like these are kind of the quote-unquote, again, my fingers are doing that quotation mark thing. They're quote-unquote factored forms. Like these are what they look like as factors. This gives you a single answer. Sometimes, though, that's not always going to be the nicest way that we want it, because we're going to actually go through and actually multiply out and want to add up a bunch of terms. So in fact, there's another form that you should also memorize. Like basically everything on this page you are responsible for memorizing and knowing on demand. Like there's no shortcut to it, you just have to know it. So this first one, basically if you multiply this guy out, you get a second form. That second form would be n squared over 2 plus n over 2. So again, where does that come from? Well, it comes from n squared over 2 plus n over 2. Like very obvious where it comes from. I'm basically just multiplying it out and giving you a term form. So this is basically the summation property in terms. This guy is the summation property in factors. So this gives you a single answer versus having the individual terms separate out. It's just a little bit different. Could be a choice depending on the problem. So first things first, there we go. We get that guy. And I'll show you these into action in just a second on the next slide. So for the second guy, for the ones when we're adding up something, the sum of a quadratic term of I squared, basically we get 3 terms. Those 3 terms are, again, if you multiply it out and simplify and stretch things apart, or tear things apart, you get n cubed over 3 plus n squared over 2 plus n over 6. So this one I find very useful. There are a lot of problems that I give you where you end up having something quadratic to sum over. So I highly recommend this one. And in fact, I'll even give you a little tip to remember everything. So n cubed over 3, so notice the powers match, plus the powers match, plus they don't match, but 6 is the common denominator for 3 and 2. So dropping in degree each time, n cubed over 3 plus n squared over 2 plus n over 6. And if you're going to multiply this whole thing out, I think it'd be 2n cubed plus 3n squared plus n all divided by 6, but who cares about that? Not important here. Last but not least, this last guy for cubed, we don't use this one as much, so if you're one of those lazy people that wants to go home and only memorize 3/5 or whatever it is that he says, obviously I would want you to cut it here. I cubed just isn't as common, although you should know it. There's no reason not to know it. And this guy, if you multiply it out, it's actually easier to multiply out because this is a perfect square binomial, and then of course you're just distributing one thing in. But either way, you end up with 3 terms also. That is an ugly looking 4, sorry. My apologies. So that's n to the 4th over 4 plus n cubed over 2 plus n squared over 4. So nowhere near as interesting at all. Not as memorable as this guy, but of course this guy's the most important one. So again, if you're trying to evaluate it, this is the least used one, so just keep that in the back of your mind. We don't pull out the cubic stuff all that often. Either way though, you must memorize all these things. And technically both of these are valuable. You need both. All of this. So you need this guy, and you need this guy, you need this guy, and you need this guy, and you need this guy, although slightly less, and you need this guy. So it's like you have a little important, but there's a little asterisk on that to say that they're the least used ones. I star to star. So either way, there we go. So now, of course, we just wrote these things down. You're just putting information down in your paper and listening to me ramble. A disembodied voice. But in fact, the question might be, well, why? What is this giving? Like, what have you done for us? Like, what have you done to make this easier on us? Like, what are we getting out of this work? I'll show you. Oh yes, welcome back. And now what we're going to do is we're going to illustrate some of the full... I can't do it. I was trying to do a British accent so it'd be a little different because this page looks just like the other one. But in fact, I'm going to blow it off. I'm just going to keep going as we go here. So what we want to do is I want to kind of show you why those summation formulas are useful. And in fact, it gets kind of dry to do this, but I'm going to go through it anyway just so you see it once, because again, I'm not here, so that way you're not wasting your time. Not that you would ever do that. Relaxing or anything when you're supposed to be learning calculus. Ridiculous. Either way, though, I just want to kind of show you how this can be useful. So first of all, what we've got up here is a summation that we might want to evaluate a little bit quicker than actually writing out 7 terms. Now again, you have to remember that this isn't truly practical. With 7 terms, we can write it out without much of an issue. We could add stuff together. It's not hard. But at the same time, what we should think about is the fact that if we had given you this as I equals 1 to 77, it might take a little bit longer. So of course, this is a way to use shortcuts for when the numbers, the bounds, are bigger. So to start off with, what would we do if we were going to use these new summation tricks with these guys? Well, first of all, we'd have to use the sum and difference property in order to separate this out. We'd have the sum from I equals 1 to 7 of I plus the sum from I equals 1 to 7 of 3. Why is this useful? Well, right off the bat, we get something that we can evaluate. This guy is just the sum of a constant. So in reality, this is now the sum of I equals 1 to 7 of I plus 3 times 7, which is 21. So again, what am I using? I'm using one of the properties, using the constant property right here. So right away, one of those properties has given us something really quick. We don't even have to think about separating or doing anything separate with the I plus 3's and adding up a bunch of terms. Already there. This guy, we also can use. This is the linear term. Like we saw this not too long ago right up here in number 4. Like it's in the sum of I is n times n plus 1 over 2. It's also n squared over 2 plus n over 2. So either way, when we go to evaluate this guy, which I'm going to do in a different color just for the sake of clarity, when we go to evaluate this guy, we can use that new formula. So to evaluate what the sum from I equals 1 to 7 of I is, we can use either n squared. So realize that the number of terms here, which is what n is representing, is 7. So we're going 7 squared over 2 plus n over 2. So plus 7 over 2 will give us 49 over 2 plus 7 over 2. And of course, what does that give us? That gives us 56 over 2, which is 28. And that means that this guy is 28. So our sum is 28 plus 21, which equals 49, which last time I checked on the second page of these notes when we were starting to do stuff, 49, 49. We've got 49 either way. So it seems like it works. It does do its job. Now, of course, some might argue that I could have evaluated this guy even easier. I could have just said that this is the same thing as n times n plus 1. So n plus 1 is 8. We'll just pretend 7 plus 1 all over 2, and gotten 56 over 2 equals 28 that way too. In this case, yeah, this would have been the easier formula. But of course, when I go forward, I'm not going to use this formula all the time, as I said. So I'm just kind of preparing you for that. Either way, we get to our value. This guy is where we really see the bang for our buck. Again, now for 5, it's not much. But for 51, say, if we were trying to add the sum of the first 51 terms of the series given by I squared, where all the terms are given by I squared, might have some problems. So of course, what is it that we're going to do here? Well, we've got that second formula to use. So in this case, 5 is my n. I've got n terms that I'm adding up, and then I'm going to use one of the two formulas. I like the one with the individual terms, although it's not as pretty. I like n cubed over 3 plus n squared over 2 plus n over 6. So this is the value of this sum. You wouldn't think so. It looks like it's a bunch of fractions, but in fact it is. It will work out all at the end. So what would I do from here? Well, I would actually have to start simplifying it. I have 125 over 3 plus 25 over 2 plus 5 over 6. And then I would go about going ahead and getting a common denominator. So that's going to give me 250 plus 75 plus 5, all divided by 6. It's going to be 325, 330 divided by 6. And of course, 330 divided by 6 is equal to 55. So we were able to find our answer there just as comfortably. Like there was nothing really difficult about that. Now, of course, you might say that, well, that's annoying. I hate fractions. I hate fractions even though I'm in calculus. Well, yeah, that's I get it. So you might want to go with the other formula, the one that's harder to memorize, and that I'm not telling you and emphasizing all the time. Well, if you want to emphasize that guy, which I even have to go back and look at, that one is the complicated thing as n plus 1 times 2n plus 1 all divided by 6. And that will also give you your formula. Or that will also give you the value of the summation. So 5 times 6 times 11 all divided by 6. Well, yeah, this one did very quickly give us our answer. So yes, for these guys it is a lot simpler to go this way. And there we go. It turns out the sum from I equals 1 to 5 of I squared is 55. And yes, again, I'm not being just a stupid teacher that's dealing with this and going, oh, you need to do it this way. Obviously, you would just add up 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. I understand this. We're preparing you for bigger sums. So there we go. We've seen that these formulas do in fact speed up the process a little bit, or more likely they just make it a little less tedious, especially when we go further, but at least for now you can agree that it takes up, it's a little bit less tedious. So here we go. Okay, so fine, it's not that much more less tedious because of the examples I chose. My bad. Let's look at some examples where this is actually useful. And in fact, let's just make it, I don't know, let's just do like one more example. So let's just stop there. Alrighty, so here is our last example. I'm going to make the goal of this last example to actually go through and show you why these summation formulas, like these shortcuts if you will, are so much nicer. The reason is obviously because we're going to pick n values. We're going to pick our upper bound with bigger and bigger numbers that make it impractical for us to do it the way we did when we first started the lesson, which was just adding up the individual terms by hand. Now you're going to see why this gives us some bang for our buck. Technically you didn't pay anything, so in fact you're kind of getting a freebie. So again, as I said at the beginning, you're welcome. So here we go. Here's our expression. What you might notice right away about this expression is it's a little bit different than the ones we had before. In particular, we actually have two variables, quote-unquote variables, my fingers are doing it again, two variables on the inside. But in fact, remember, n isn't really a variable here. It's a constant. It represents our bound. So if we were adding up I equals 1 to, say, 42, this would be 42 squared on the bottom. Why would we do it that way? Patience, young Padawan. Or patience, young Padawan has. That was Yoda, if you weren't sure. That was Yoda. Yeah. So anyway, back here we are. We're trying to add up and summate these things. So what I'm going to do is, because I've got this n that's going to be changing actually a little bit, I'm going to wait on that. I'm not going to plug in 10 and then evaluate it each time, because that could be kind of ugly. Instead, what I'm going to do is I'm going to evaluate the sum once, using the shortcuts and simplifying as best I can, and then I'm going to plug in the 3 values, and then maybe we'll start to see something interesting happening here. So let's do that. Let's figure out how we can simplify this guy. So what is it that this guy is going to simplify to? So how can we simplify that? Well, basically the first thing that I'm going to do as I simplify it is I'm going to pull this guy out. As I said, n is a constant. It just represents our upper bound. So I'm going to pull that out as though it were just a scalar, because in reality it is. It's just a scalar that's dependent on how many things we're choosing. So I'm going to pull it out in front. 1 over n squared times I equals 1 to n of I plus 1. I added the parentheses so it was clear that stuff was on the inside. You'll thank me later. And so there we go. Now we've got a scalar out in front, 1 over n squared. I mean, who cares? It's got an n. Don't be prejudiced like that. And now I'm going to go through and I'm going to evaluate the sum on the inside. So how am I going to do that? Well, again, I've got to be a little bit careful. So I've got 1 over n squared times the sum of the first part. So I'm going to use that one. So I equals 1 to n. And then I'm going to add 1 over n squared times the sum of 1 from I equals 1 to n. And now I've just got to go through and evaluate each of these parts. So what is this thing equal to, and what is this thing equal to? And now I'm going to do it a little bit weird. I'm going to actually do it with the individual terms. Obviously some people might choose to do it differently. It's just a personal choice. Don't argue with my personal choice. So what do we have here? Well, first of all, we've got 1 over n squared. That part's not changing. What we want to look at is what is that guy equal to? Actually, I'm going to change color. I think color helps here. Okay, so what is that guy equal to? Well, the sum from 1 to n of I is just going to be that first one. It's either n times n plus 1 over 2, or the one I like better, n squared over 2 plus n over 2. So got it. Again, I'm just using the formula because I've memorized it, because it's in my... Could you hear that knocking noise on my head? Because it's in my head, I can actually do that. For the next guy, I'm also going to be adding 1 over n squared times something. I just have to look at what that other formula is actually equal to. So let's use green again. Green is fun, so let's do that. So what is this formula here? Well, we're adding up 1 n times. That's just n times 1. So easy enough, simple enough, I can do that. So now what we're going to do is we're just going to simplify, see what we've got. So in this first guy, when I multiply and distribute this guy in, 1 over n squared times n squared over n squared, that's going to be equal to n squared over 2n squared, which is just equal to 1/2. Usually I'll be more careful, but you'll see that tomorrow when I actually do this in class with the real problems. On the second one, I'm going to get plus 1 over 2n. For the last guy, I've got basically n, so when I multiply this in here, I'll have n over n squared, which is just equal to 1 over n. So now this guy is basically there. The only thing I could do is simplify it a little bit, so I'm going to do that. I'm going to get this 1/2 stays the same. I'm not going to change that. You'll see why in a second. This is an intentional thing. And then this guy, if I multiply up and down by 2, why would I do that? Well, again, just for simplicity, I'll have 2 over 2n plus 1 over 2n is plus 3 over 2n. Nothing particularly fancy. And so this is what my sum will always equal to for any value of n. Interesting now. So this is the thing I've got to evaluate. So the question then becomes, well, what happens with the different values of n? So what happens when n equals 10? What happens when n equals 100? And what happens when n equals 100,000? Again, you might say that's a ridiculous job of spacing, and you're absolutely right. I'm going to fix it right now. There we go. So what are our particular values here? Well, actually, it's kind of interesting. This goes pretty fast. For this first guy, for n equals 10, we're going to get 1/2 plus 3 over 20, and that's going to equal to, multiplying up and down by 10, what is that? 13? God, I'm tired. So that'll be 10 plus 3, that's 13 over 20. So, okay, whatever. Interesting. 13 over 20. That's approximately, well, it's not approximately, but whatever. It's equal to 0.65. So for the next one, what happens with 100? Well, we get 1/2 plus 3 over 200, and that is equal to 103 over 200. So it doesn't seem like that's very remarkable at all. In fact, it's not particularly remarkable. But we could get an approximate value, and I'm not going to pretend that I can do that in my head. I'm not going to cheat like that. That'd just be rude. 103 divided by 200 is equal to 0.515. Ah, this pen is something else. Don't have this problem in school. There we go. 0.515. And then last but not least, 1/2 plus 3 over 200,000. Well, at this point, I'm not going to do a whole lot. Obviously, this is equal to 100,000 3 over 200,000. And of course, I'm just going to go ahead and say that that's pretty close to 0.500 something. So we went to say 3 significant figures. So there we go. We evaluated it. As far as what we're supposed to do today, hey, we've done our job completely. We were able to evaluate the sum and evaluate it for 3 different values of n, for 3 different upper bounds. The question is now, why might we have done this? Like, what might have been the purpose of looking at this? And what I would hope you would recognize, because you all passed the first half of calculus, most of you with flying colors, I would hope that what you're recognizing is that as we go, there's a certain kind of behavior happening. As n gets bigger, so as n approaches, say, I don't know, what's a really big number? You could think of infinity. Hey, good call. As n approaches infinity, notice that our sum is doing something else. What is that something? Here, let me call on someone. No, that's just ridiculous. That would be crazy. No one's going to answer me. Or even if you do, I'm not going to hear you and I'd be talking over you. I apologize. Obviously, as n gets bigger, the sum approaches a value. That value is 1/2. Now, of course, how might we have been able to get that out of this information? Well, take a look right here. I'll erase this in a second. I'm just going to do it because this is just talking point at this point. We're getting ourselves ready for tomorrow's lesson when we go a little further with it. We'll look at our formula. This is our sum. Do you agree this is our sum? Yes, Mr. Chow, this is our sum. So yeah, here we go. Great job. Exactly. You guys are right. This is our sum. Well, our question might be, well, we're saying what's happening as n gets bigger. In other words, what is the limit as n goes to infinity? The limit as n goes to infinity is going to be 1/2 plus 3 over a gigantic number is 0. Our limit is going to 1/2. So in fact, this does make sense. Like what we're seeing here is this limiting, this process, the summation, whatever this means, which we'll again talk about in the future. You don't have to worry about that now. What happens is we can actually evaluate limits of these summations and figure out what happens when we pick bigger and bigger n's. Like what happens is we let n get bigger and bigger. Now the question might be, well, what's going to use those? Like what am I going to use those for? Like what would we ever need to make n bigger for? Like n's just smack dab in the middle of the alphabet. I mean, who really cares? Yeah, that's true. I can buy that. Actually, I'm going to leave that there. It looks really nice. So yes, so what does it mean? I got distracted by pretty colors. So what does it mean? Well, in reality, you have to kind of think about where we might use n. Like where might it matter, or where might we change the number of things that we're doing it for? And the answer to that question is not an easy one, but it has a lot to do with one of the key problems of calculus. Not the tangent line problem, but the other problem of calculus, which I mentioned one time at the very beginning of the year. So if you took Calc Prep last term, you might already know a little bit about it. But the idea is there's another very important concept that is related to derivatives, not as easy to see. I was going to say tangentially, but that would just have been a pun, because tangents, get it. The idea is there is a connection here. It's just going to take us a little bit to get there. And we're going to have to build up some ground level stuff before we get there. As far as what you need to know, you've seen it all here. Basically, we've gone through, and in today's lesson, we have started by reminding you a little bit about sigma notation, because it might have been a while for some of you. Talked about the pieces of sigma notation, and then we evaluated it using basically what the meaning of the notation is. Adding stuff up. Then from there, we looked at some of the properties of summation that will allow us to take care of business with a lot of these things. So in particular, we talked about some of the constant rule, the constant property, to get multiple properties, some difference property, and then 3 things that you have to memorize. What is it that you have to do, Mr. Steele? Oh, you have to memorize it. Basically 6 things, 6 versions, or 3 different properties, each with 2 versions, that you need to memorize and be able to use, because they shorten the process. Not for easy problems like these guys, but for the harder problems when we get bigger and bigger values of n. They allow us to simplify things really quickly. And why might we want to do that? Well, for whatever ambiguous reason out there, we might want to eventually take the limit as n goes to infinity for one of these sums. We'll see why we want to do that. It has to do with a key problem in calculus. The idea, though, is that you've done everything you need to. We've gotten through everything here. And now at this point, if there's any time left, then you are welcome to work on your homework, or work on this sample study guide if you didn't get one of those. Whatever the case may be, it's your call. The idea, though, is you've just made a day when you were going to have a sub into one where you've actually gotten a quick little refresher and you're able to get started and work on your homework. So either way, I hope this has been beneficial. Hope it's been entertaining. I know it's not easy. I didn't use a lot of clip art. Could throw something up here now, but it'd just be beside the point. So instead, I'm just going to say this is the end of my portion of your lesson today. This is Mr. Steele. Enjoy the rest of your day, and I will see you tomorrow. Have a good morning. Have a good morning. Bye.